Hello and welcome to CMG's webinar on latest advancements in modeling and optimizing hydraulic fractures. My name is Anjani Kumar. I'm the Vice President of Consulting Support and Training at CMG. I'm pleased to introduce Alex Nowelski. He's a Senior Reservoir Simulation Engineer and who will be presenting today's webinar. Alex holds a Bachelor of Science degree in Oil and Gas Engineering from University of Calgary and has been with CMG for past 7 years. Alex is the domain expert in the simulation of unconventional oil and gas reservoirs, hydraulic fracturing, optimization, and uncertainty analysis. Before we begin, I'd like to inform you that we will have a question and answer session at the end of the presentation. However, at any time, if you have any questions, you can submit them through the chat window on your screen that is present on the right of your screen. Over to you, Alex.
Thank you, Anjani. Once again, my name is Alex Nowelski, and today I'll be going over the latest advancements in modeling and optimizing hydraulic fractures. So to start off with, I'll be going over with a brief overview of shale oil and gas production. We'll also look at why we would want to use reservoir simulation to model tight reservoirs, including shales. We'll look at what types of physics and mechanisms are being modeled in these types of plays. And we'll also look at some of the new advances in modeling hydraulic fractures, which we've added over the past couple years. As well, we'll look at how simulation can help in understanding the physics and production from these reservoirs. And we'll also look at some of the challenges, opportunities, and lessons learned over the years. Finally, we'll see why we would want to use CMG specifically for modeling tight and shale plays. So to start off with, here I have a map of most of the shale plays in North America. So we can see that we have things all across the continent, such as the Barnett Shales, Eagle Ford, Marcellus, Bakken, and if you're in Canada, things such as the Horn River and the Montney. As well as you all know, there's been quite a large growth in this area over the past few years. Starting in about 2006 or 2007 is when things really started to take off. And we can see both in the oil production and in gas production, things have been growing steadily. As well, current predictions also expect this trend to continue, with shale gas production continuing to grow over the next coming decades. And as well, tight oil is expected to follow a similar trend. And here we have it compared to the U.S. maximum production level of 9.6 million barrels per day in 1970. So current expectations are that we will once again reach that maximum production level within the next few years. So next we'll look at why we would want to use reservoir simulation for modeling these types of tight reservoirs. For one thing, there's a very long time to reach pseudo-steady state in these types of reservoirs, so oftentimes we're continually in a transient production period. So oftentimes analytical techniques or other methods that have this steady state assumption will fail when we're looking at tight reservoirs. However, when we look at simulation, depending on the grid sizing used, it comes very naturally. As well, we may need to account for things such as multi-phase flow if we have liquids-rich plays, such as gas condensates or volatile oils. As well, things such as non-Darcy or turbulent flow in our fractures when we reach high velocities. Things such as multi-component phase behavior, absorption, and diffusion. When we get up to these high pressures, we often have more than just the free gas. We have gas absorbing onto the rock surface. In some instances, we may also have compaction of fractures, where the fractures may be closing over time as pressure drops or stresses change. And the reservoir, we know, is not homogeneous. So throughout the reservoir, we have changing properties such as varying porosity and permeability. Even from one end of a well to another, we can see very large changes in these properties. And as well, due to this, also the fractures are going to be quite different. In one area, we may have long fractures, where in another area, we may have much shorter fractures. So along the well, we're not going to have one single size of fracture or one set of fracture properties. And as well, we may want to consider things such as geomechanical effects, where we may have changing properties due to changes in stress regimes. And in some instances, we may have frac fluid interacting with the native reservoir fluids. So we may want to take into account the geochemical reactions which may be occurring. As well, the way that the wells are completed and designed, we're going to have things such as interference between different stages of the well, as well as between wells on the same pad. And of course, wells are not all drilled with uniform spacing between them. In some instances, we may have wells closer to each other than others. So assuming sort of uniform properties may not always be accurate. In some instances, we may also have cases where we refrac the wells or where we have infill drilling, where we may have changes over time that may not be predictable. And as well, we want to be able to interpret production surveillance data. So if we have varying degrees of production from the different areas of the well, we know that the fracture properties are likely also different. So by incorporating this type of surveillance data, we can better understand how the fractures are being created. And of course, all these properties that I've gone over need to be simultaneously accounted for. So we have all sorts of complex behavior occurring in the reservoir, and of course, we need to account for all of these things for accurate predictions. So when we look at a typical reservoir model for an unconventional field, there's a few things that we will always be adding to the models. In the reservoir description, we'll be adding things such as our matrix porosity and permeability, but we also need to account for the properties of the fractures. So we want to put in properties of permeability for our natural fractures as well as our prop fractures. If we have closure of fractures, we need to account for pore volume compaction and dilation, which can also affect the permeability as well. If we have high velocities within our fractures, we can also encounter non-Darcy or turbulent flow, which can hinder production. And looking at the phase behavior, we need to account for things like going over the dew point or the bubble point. So depending on the type of fluid that's in the reservoir, will determine how we want to model this when we look at the simulation. So if we have a dry gas or a black oil, we may use our IMEX simulator, which can typically be used if we're looking at primary production mechanisms. If we have more advanced mechanisms, such as enhanced oil recovery, or we have near critical fluids, then we may want to look at an equation of state simulator, such as GEM. So this is especially important if we're doing things such as miscible gas injection EOR, or if we have a gas condensate or a volatile oil fluid in our reservoir. It's much more important to take into account the changes in composition over time. Following this, there's a few commonly modeled physics which may not be included in all simulation cases. So one of these includes adsorbed components and being able to monitor that absorption over time. So this can be used in simple cases where we just want to have absorption of the gas phase only, such as when we're in dry gas or shale gas reservoirs. As well, we may also want to account for multi-component gases and liquids. So within GEM, we can also provide different absorption properties for each component. So on the diagram on the right-hand side, we can see how the different properties may absorb at different volumes versus pressure. As well, when we have multiple fluids in our reservoir, we may also need to account for things such as diffusion. So this would be important if we have, say, a multi-component gas, or if we're doing things such as miscible gas injection, EOR, where once we inject the fluids into the reservoir, they may diffuse away from the well. When looking at the rock physics, we would want to account for things such as our relative permeability and capillary pressure. And we may also have different behavior between our matrix and our fractures. So within the tight rock, we may have one set of relative permeability curves and capillary pressure. However, when we look at the fractures, we may have more straight line relative permeability curves with little or no capillary pressure effects. So within the simulation model, we can account for both of these types of behaviors simultaneously. It's also important when we look at the gridding for the model to be able to have gridding that accurately accounts for the fluid flow near the fractures. What we typically recommend with CMG is to use the LSLR-DK method or the Tartan grid method for modeling these types of propped fractures. This method incorporates local grid refinement around the hydraulic fractures with logarithmic spacing of the gridding so that we have small gridding near the fractures where we're going to have the largest pressure and saturation changes, but we can also have larger gridding away from the fractures where the velocities will be lower. So this allows us to accurately account for the transient flow behavior while still having reasonable simulation runtimes. We can also use the dual permeability system to account for the natural fracture flow away from our main prop fractures. So this method will allow us to account for transient multi-phase fluid flow from matrix and natural fractures as well as from the matrix to the prop fractures. We can also add in corrections to account for non-Darcy flow in the prop fractures where we would reach high velocities near the well laterals. Some other things that we can also do with our models is initialize the hydraulic fractures with frac fluid. This allows us to better account for the changes in water saturation within our hydraulic fractures, and we can also account for the frac fluid flowback. So I'm just going to go over quickly how we model our gridding when we're looking at hydraulic fractures. So on the diagram on the left-hand side, we have a stimulated reservoir volume. And if I zoom in on one of the elements within the stimulated reservoir volume, we can better see how the gridding is set up. So in the dark red color on the right-hand side, we can see our prop fractures being defined. And then in the light blue color, we have our rock matrix. What we can see away from the fractures is logarithmically spaced gridding, which is very fine near the fractures, but gets larger as we go further away from the fractures. Near the fractures is where we're going to have the largest changes in pressure, as well as changes in fluid saturation as pressure goes below the bubble point. So this allows us to accurately account for this multi-phase flow, as well as the transient flow behavior around the fractures. We can also specify different fracture geometries depending on the native state of the reservoir and the stress regimes. So in more simple cases where we have one dominant stress direction, we may have planar fractures being created in our reservoir. However, in some cases where we have more uniform stress regimes, or if we have more natural fracturing occurring, we can also have more complex networks of fractures. So both of these methods are easily available within CMG. When we look at the different products that we would want to use for these types of reservoirs, the two main simulators that we would want to use would be GEM and IMEX. GEM is our compositional and unconventional reservoir simulator, which can account for multiple components within the reservoir and is especially useful for near critical fluids or looking at miscible gas EOR. There's also IMEX, which is our three-phase black oil reservoir simulator, which can be used for black oil type reservoirs or looking at dry gases. Oftentimes we also want to do more advanced processes or more advanced analysis. CMOST is another tool that we can use to automate some of these processes to save you time. So it can be used for processes such as sensitivity analysis, history matching, optimization, and uncertainty assessment. CMOST will take your base data sets and will modify them according to the method that you're using, and will automatically create new data sets, simulate them, as well as review the results. This can greatly enhance your workflow by reducing the amount of time necessary to spend on these tasks. As well, we also have our builder software, which we use to input all of the information into our simulation models, as well as add in the hydraulic fractures. Later on in this webinar, I'll be going through a demonstration as to how we can add in the hydraulic fractures into our unconventional reservoirs. So when comparing the two simulators, there's a lot of common features, but there's a few things that will differentiate between the type of simulator that you may want to use. With IMEX, typically we will use this in primary production type processes. However, if we're doing more advanced mechanisms, or we want to account for multiple components in our models, we can also use GEM, which can also account for things such as geomechanics or geochemical reactions. Over the years, CMG has also been improving our software and adding in some of the latest advances and latest improvements in technology from the field. Initially, we added in features for modeling hydraulic fractures in 2008, when most of the wells being drilled were vertical wells. Following the changes in industry, more and more operators moved over to horizontal wells with multi-stage fractures. So in the following year, we improved our technology to be able to account for these types of wells. Over the years, we've added in various other improvements. Most recently, we've adjusted the definitions of the hydraulic fractures, making it easier to edit your models, as well as resulting in smaller file sizes. One other thing that we can also add, which we've added in a few years ago, is the ability to incorporate microseismic data into your simulation modeling building. Often this information is captured during the stimulation process, which can then be used to estimate the extent of the unpropped SRV during pumping, as well as the geometry of the fractures that will be generated. During treatment, this is often required to monitor or even control the treatment, and we can easily incorporate this information into Builder's workflow using the Microseismic import wizard. In the diagram on the right-hand side, we've got a horizontal well with 4 stages of fractures added, as well as the microseismic data associated with each of those stages. As you can see, we can quickly and easily generate the fracture network around the microseismic cloud, so we can get a better approximation as to where the fluid is coming from in the reservoir. Additionally, we can also account for geomechanical effects in the reservoir. So we can include things such as permeability changes with hysteresis as a function of stress change during production and shut-in periods. Oftentimes, as we start producing from the reservoirs, the stresses will change in the reservoir, and we may have fracture closure. As well, we may have things such as proppant crushing and embedment, which can change the permeability over time. Oftentimes, when we're doing this to model the hydraulic fractures, we'll be using the Barton-Bandis method, which allows us to monitor the stress changes and be able to see where the fracture would propagate through the reservoir. In the diagram at the lower left, we have a simple case that we've generated modeling the propagation of the fractures upon injection. In this first example, we have a uniform stress regime, and we can see that what is created is a network of fractures, but we don't see really any particular direction that it's going in. If we then try another case where we adjust the stress regime, so we have a dominant stress direction in the north-south direction, we can see that as the fracture propagates with the same sort of conditions as the first case, we see the fractures propagating primarily, again, in that north-south direction. This would represent more of the planar fractures, where the initial case on the left side would represent more of a network of fractures being generated. So next I'd like to go through some of the new advancements in the hydraulic fracturing modeling, which have been added over the previous year. If you're familiar with the existing method that we used, oftentimes when we looked at the data sets, there could be quite a lot of information stored in the data sets related to the hydraulic fractures. So here we have the definition for one fracture in our model. And if we look throughout the data set, there'll be other areas where we'll see information related to the fractures. So here we have the definition for the refinement around one of the fractures in one of the models. As you can see, it's quite a lot of information, and not all of it is really representative or useful to the user. It's more information used by the simulator. So in a case with 17 wells and 117 stages, this resulted in about 720 lines added to the input deck by Builder. So over the year, we have worked on reducing the file size and getting more concise fracture definitions. So this allows us to actually identify the different properties of the fracture, such as half-length or permeability, and have those definitions listed directly in the data set, as opposed to having several properties related to it. So what you'll see is also the refinement definitions will be removed from the data set, as well as some of the other properties that would have previously been generated. So this type of information will now be generated by the simulator upon simulator initialization. So this allows us to keep our data sets much smaller while still having the same information given to the simulator. Builder and the simulators will also share the same code, so what you see being defined in Builder will be exactly what the simulator will take in when it initializes. We also added in a couple new features to make it easier to work with the hydraulic fracture models. This includes things such as fracture templates, where we can define one fracture with a set of properties, and these properties can be reused on other stages on a well, or even on other wells in our reservoir on the same pad. It also gives a single place to adjust the model, especially if we're looking at using automated processes such as CMOST. The hydraulic fractures are also now a simulator keyword, so you'll see specific definitions now listed in the data sets. So instead of seeing permeability changes in refinement, you'll now see more recognizable things such as half-length, height, as well as the fracture properties such as width and permeability. The fractures will also now be defined as an object, which allows us to easier adjust some of the other properties associated with the hydraulic fractures. So for example, if we wanted to have different relative permeability curves for our matrix and for our hydraulic fractures, we can now refer to the fracture by name and specify one set of relative permeabilities for the matrix and one set of relative permeabilities for the fracture. It can also be used for other things such as initial fluid initialization. So now we'll see the definition for one well using our new methodology. So you'll see things such as our primary fracture width, the permeability associated with the fracture, and we can also have conductivity gradients along our fracture. So oftentimes the fracture will be wider and more conductive near the well, and will lose conductivity as we go towards the fracture tips. By being able to provide a permeability at the center of the fracture as well as a permeability at the tip, we can accordingly adjust the conductivity along that fracture. As well, we can define things such as our half-length, the direction of the fracture, whether you have a transverse or a longitudinal fracture, as well as the fracture height defined by the number of layers above the well that the fracture will propagate and the number of layers below the well. Builder will also generate some effective permeabilities that will be used by the simulator. The last thing that we need to define with our fractures, now that we have the properties defined, is where along the wells we want our fractures to be placed. For doing this, we'll define our fracture name, the well that we want to associate the fracture with, the number of fractures that we want to have on the well, as well as the placement of these fractures, and then finally we'll associate the template that we've generated to the fracture that we're creating. We'll also give the fracture a name so that if we want to define other properties, we can refer to this fracture by its unique name. So here, if we want to adjust some of the properties of this particular fracture, later on we can refer to the fracture name, which is well 1, frac 1, and adjust the properties accordingly. So overall, in the case with 4 well stages, the previous methodology would have about 15,000 lines in the data set associated with the fractures, where the new methodology will reduce that down to about 31 lines. So overall, most people only will be looking at this in Builder, but what this will represent is faster generations of the fractures, faster time to save the models, as well as a faster time to reload the models. And like I said, now that we can refer to the fractures by name, we can associate other properties to these fractures, such as different relative permeability tables, different rock types or compaction tables for modeling the closure of fractures, as well as specifying different initial fluid saturations so we can initialize the hydraulic fractures with the frac fluid. And really any of the other properties that we add into our simulation model, we can also specify using these block groups. You can also apply different properties to different areas around the fractures. So whether we want to change the properties of the matrix around the fractures or the natural fractures in that area, we can do so. We can also adjust the properties in the main fracture conduit as well as the region around the fractures. If you do have older data sets that used our previous methodology, these data sets can still be used. So if you open up the data set in Builder or Results 3D, they'll be exactly the same as were previous. As well, older data sets can run with the newer simulator with no changes necessary to the data set. However, if you do want to take advantage of the new syntax, you can automatically convert the data sets to the new method. All you need to do for this is open up your previous data sets in Builder, and when the data set is saved, it will automatically be converted. So this may make it easier and faster to work with your previously created data sets. So now I'm going to go through a quick demo where we see how we can add in a set of hydraulic fractures into a well pad. So I'm going to switch my screen over to a Builder model which I've previously generated. So this model has the properties of a typical dry gas or a shale gas reservoir. We can see that we have 5 horizontal wells which are spaced 500 meters apart. So at this point we've defined most of the reservoir properties, and what's remaining is to define the hydraulic fractures in this model. So I'm going to switch down to the 2D view, and then we'll go through the process of adding in our hydraulic fractures. So to add in the hydraulic fractures, I'm going to open up the hydraulic fracturing window. And what you'll see when you open up this window is the 5 wells being defined as well as their original completion dates. To start off with, I'm going to generate a template which we can use to apply to each of these wells. So on the Templates tab, I'm going to add in a new template where I can define the properties associated with the fracture. So first I'm going to define the fracture width at 2 millimeters and the intrinsic permeability at 32,000 millidarcies. Builder will automatically generate an effective permeability which is used by the simulator. Next, if we want to apply a gradient of conductivity along the fracture, we can also apply a permeability at the tips of our fractures. So here I'm going to specify the permeability at the tip as 3,000 millidarcies. As well, in some instances, we may have some secondary fractures or some enhanced natural fractures around our main prop fractures. So if we'd like, we can also define the properties of those fractures. For this, I'm going to put in a secondary fracture width of 0.5 millimeter with an intrinsic permeability of 500 millidarcies. Next, we're going to define the geometry of the fractures. In this case, I want to have transverse fractures, so I'm going to select that the fracture should be oriented in the I direction. I can also adjust the refinement settings around the fractures. In this case, I'm just going to leave it at the default settings. And then I'm going to specify the fracture half length, which in this case will be 100 meters. Next, I'll specify the fracture height by defining the number of layers above and below the well that the fracture will propagate. So we'll say that the fracture will go 1 layer above the well and 2 layers below. So now I have completed my fracture definition. Next, I'll apply the fracture to one of the wells. So I'm going to start with horizontal well 1, and we have the initial completion date for the well. If we want to add in a new date, we can also select to add in a new fracture date if the well was fractured at a later date. Next, I'll specify whether I want to have a planar fracture stage or a complex fracture stage. In this first case, I'll select a new planar fracture stage. So when generating the fracture, I can select from the fracture template, which I've just created. And next, I'll need to specify where along the well I want to place the fractures. In this instance, I'm going to apply a fracture spacing along the well, which is going to be 100 meters. When I click Apply, you'll see that the fractures will be added next to or along horizontal well 1. So once that's generated, we can see all along the well, we've got various fractures being added. And now I'll zoom in on the well to see exactly what has been modified. So when I zoom in on the well, we can see in the red color the fracture permeability. And as well, you can see it's varying as we go along the length of the fracture, representing the fracture conductivity gradient. Next, I'll re-enable the gridding on my model so that we can better see the refinement that was added around the fractures. So when I zoom in on the fracture, we can see the local grid refinement has been added around the fracture with logarithmic spacing, allowing us for smaller gridding near the fracture and larger gridding as we go away from the fracture. This allows us to accurately calculate the transient flow behavior while still having reasonable run times. So these types of properties would be added around each of the fractures in the model. So next I'll add in some fractures to horizontal well 2. I'll select the completion date for well 2, add in a new horizontal or a new planar fracture. And since I've already created a fracture definition, I can quickly just select the previous definition that I've created. In this case, I'm going to apply a different fracture spacing. I'll select 75 meters in this case and apply the settings. So now we can see we've added in the fractures along the well, and in this case the fractures are spaced slightly closer than in the first instance. For the third well, I'm going to adjust my settings for my fracture by creating a new template for that fracture. In this case, I want all the properties to be the same, except I want a different fracture half length. So what I'll do is I'll copy my initial fracture settings that I created, and I'll redefine this new fracture template. So I'll give it a new name. In this case, I'm going to set the half length to 160 meters. So I'll give it a descriptive name for this. Next, I'll scroll down to the property that I wanted to change, which is the fracture half length, and I'll apply the new setting, so 160 meters. As well, if I want to add in any other properties associated with the well, I can do so in the lower section. So for example, if I wanted to adjust the relative permeability sets for the matrix and the fracture, I can select from the properties listed. So I'll select relative permeability set number. I'll use set number 1, which represents the relative permeability behavior in the matrix for the matrix area. And I'll select set number 2, which has different relative permeability to represent the behavior within the hydraulic fractures. So next I'll go back to horizontal well 3, and I'll add in a new planar fracture stage. When I select from the templates, now I have all the templates that were created. So we'll select the new template with the 160 meter half length. And once again, I'll specify the fracture spacing. In this case, I'll say 125 meters. So now that this fracture has been added, we can see that the fracture is slightly wider than it was previously, as well as spaced out a little bit further away from each other. I'll just zoom in on the model so we can get a better look of that. Once again, we can see the longer half length as well as the wider spacing between our fractures. For well number 4, I'll show how to add in a complex fracture stage. So this time, instead of selecting a new planar fracture stage, I can select a new complex fracture stage. If you have microseismic data available to you, you can import the data in the top section and be able to use this data to define the stimulated reservoir region. If you don't have this data or you want to adjust it manually, you can always click on the reservoir and select where you want your stimulated region to be. So I'm going to select a region around horizontal well 4, and I'm going to add in the blocks to the stimulated reservoir region. As well, I can make further adjustments, adding in larger stimulated regions in one area, and I can remove some blocks from another region to make it a smaller stimulated reservoir region. Once you're satisfied with the settings associated with the stimulated reservoir volume, we can then specify the properties associated with it. So I'll click Apply, and then I'll go down to the associated properties. So once again, I'll specify some intrinsic properties of my fracture, such as the width at 2 millimeters, and the permeability at 32,000 millidarcies. As well, I have the capability of specifying the secondary fracture properties. So I'll select the secondary fracture width as 0.5 millimeter with 500 millidarcy permeability. When I click Apply, it will add in all the associated options with these fractures. So once again, I'll zoom in on the fracture and we can see what has been added to these to this network. So in the dark red color, we can see my prop fractures within that stimulated reservoir volume. As well, we can see the local grid refinement added around each of these different fracture elements with logarithmic spacing, giving us different permeabilities as we go away from the fractures. For well number 5, I'm once again going to add in a planar fracture stage, and we can finish off adding in the fractures to this path. So I can select from any of the defined templates. I'll select the first template, and in this case I'll specify a fracture spacing of 100 meters. As well, if you want to adjust the properties of any individual fracture, you can go select the individual fracture and select from any of the properties and modify their settings. So if we want a different conductivity of any of these fractures, we can go and select them and put in different permeabilities. So you've seen how quick and easy it is to add in a set of fractures into a whole pad within 10 minutes. So next we'll look at and see how we can automate some of the different engineering processes to speed up some of your analysis. So oftentimes we'll also use CMOST, which is our product to assist in sensitivity analysis, history matching, optimization, and uncertainty assessment. What CMOST will do is it will take a base data set like we've just created and will automatically adjust some of the settings within the ranges that you provide. This allows you to do things such as sensitivity analysis, where we can see how the different inputs into our simulation model will affect the outcomes, such as our total production or our ultimate recovery. We can also do things such as automated history matching, where CMOST will use its optimization algorithms to tune your data set to match your measured results from the field. Once we have a history match model, we can also look at doing optimization, where we can look at different well configurations or completion configurations. So with this, we can look at different well spacings or fracture spacings and find out which one is the most economical. We can also look at things such as uncertainty assessment, where we take some of the uncertainty in our input variables, such as our matrix porosity and permeability, and see how that will affect our ultimate recovery. This will provide us with a probability distribution so we can see our P10, P50, and P90 outcomes. When we're looking at our unconventional reservoirs, oftentimes we might want to adjust some of the properties associated with the fractures. So in doing this, we can really adjust any of the properties associated with the fractures. Things such as half length, width, permeability, spacing, height, as well as the permeability gradient. And if we specified secondary fracture properties, we can also adjust the width and the permeability of these secondary fractures. If you have incorporated microseismic data in order to size your stimulated reservoir volume, you can also incorporate this into CMOST by adjusting the size of the stimulated reservoir volume based on imported data such as moment or confidence from that microseismic. So to do this, CMOST needs a master data set to be generated, which is used as a template for creating new data sets while specifying what things in the model you would want to adjust. To generate this template or this master data set, it can be done in a variety of different ways. One way is to do it manually through a text editor. We can also use the CMOST text editor, which simplifies the process. Or we can also use Builder for selecting the different items that we would want to change in our model. So next I'm going to go through how we would take one of our simulation models and apply it to CMOST. So once we've created a base model like we've just done in this last example, we can go and add in a CMOST master data set for use with CMOST. So under the Tools menu, we can go to the CMOST Master Dataset Creator. And we can really select from many of the reservoir properties that we've defined in our simulation model. In this case, we're going to specifically look at how we can adjust the hydraulic fracture properties. So I'm going to look at adjusting the planar fracture properties. And it will list out each of the templates that I've defined. So if I wanted to change the properties of one of the templates, such as the permeability, I can select the permeability that has been defined and then add it in as a CMOST parameter. If I want to change some of the other properties, such as the half length, I can do so as well, or even things such as the fracture height. As well, if we wanted to look at the spacing between our fractures, we can also add this in as a new property. So here I have the fracture spacing between the wells, and I can add this in as a new CMOST parameter. This can be useful if we're doing things such as optimization, where we would want to adjust the spacing between different fractures. Once we've selected everything in the model that we might want to adjust, I can save this as a new file, which CMOST can then use to generate new data sets, run the simulations, and analyze the results. So next we'll see how we can put CMOST to use in order to optimize some of our processes. One of the common tasks that can take quite a lot of time if we're doing manually is things such as history matching. This involves adjusting the inputs into our simulation model to match some of the historical data found in the field. So matching things such as our oil production or our gas production, or things such as your well pressures. With CMOST, we can specify the types of things that we want to change in our model, and CMOST will automatically select from ranges that you provide to be able to find the best combinations that will provide a history match. With doing this, we only need to specify the initial inputs, and CMOST will do all the rest using its optimization algorithms. We can see here that it's found 10 different history matches with different properties associated with each of these matches. This can then be used to provide a range of forecasts to give a better estimate of our estimated ultimate recovery. With this, the engineer only has to monitor the history match process and is free to work on other processes as CMOST does most of the work. As well, we may want to do things such as optimization. In this case, we're going to look at an optimization where we looked at doing different well spacings with different amounts of wells per section. Here we've analyzed between 1 well per section up to 9 wells per section, along with the varying production associated with each case. CMOST will generate these cases as well as analyze the results and compare them to the drilling and completion costs associated with each well. We can then look at the NPV of each case and see which case is optimal. So we can see initially as we keep adding wells, we see an improvement in our NPV until we reach 7 wells per section, which in this case has the maximum NPV. When using reservoir simulation, we can better understand and predict shale and well production while accounting for various different mechanisms. So things such as reservoir heterogeneity, well complexity, where different wells may be completed differently or at different times. We can accurately account for the physics of fluid flow and heat flow, especially when we have multi-phase behavior, as well as accounting for different effects such as geomechanical or geochemical effects. It also allows us to enable physics-based analysis and optimization of these plays in an efficient manner when using CMOST, which can be used in a variety of different ways. So things such as EOR calculations and validation, well completion design optimization, as well as well spacing optimization. So next I'll go through some of the challenges, opportunities, and lessons learned over the past few years. Oftentimes when we look at modeling these types of reservoirs, we encounter a variety of different challenges. These can include things such as lack of PVT data for shale liquids plays, which can affect our fluid characterization in the reservoir. As well, oftentimes there's a lack of bottom hole pressure data. Oftentimes we may have measurements at surface, but may need to use correlations to get properties downhole. With these types of plays, the BHP data is very important since we can get a variety of different history matches when only looking at the oil or gas production. But the BHP data will really define what's occurring in the reservoir and help us better understand the fracture network as well as the reservoir response. As well, when defining the reservoir properties, oftentimes the shale reservoir property measurement is uncertain, costly, and time-consuming, which can make it very difficult to obtain accurate measurements of things such as porosity and permeability. As well, microseismic data acquisition and analysis is not well understood and not universally accepted. And in more advanced cases where we have a lot of natural fracturing or uncertainty in our reservoir properties, Frac design treatment software often lacks proper modeling of the initialization and propagation of naturally fractured rocks. As well, looking at some of the other properties of the reservoir, it can also be costly to acquire geomechanical properties, and often the initial stress states in the reservoir is unknown. As well, there can be a lack of staff to perform reservoir modeling work. As well, not enough people to do things such as that are cross-trained in production and well completions technology or geomechanics. Oftentimes what we see is technology discipline silos which inhibit learning between companies or even within the same companies. Oftentimes we can see that people working at one play may not be interacting with people in another play, even within the same company. We've also identified several different opportunities which we can use when looking at reservoir modeling. These can include things such as constraining reservoir parameters using known relationships between frac geometry, width, permeability, and density. Oftentimes people look at these things as separate entities. However, we know that these should not be independent variables. As well, we can also constrain rock physics relationships, where things such as relative permeability and capillary pressure are definitely related functions. And we can also better characterize our natural fracture network using discrete fracture network modeling. We can incorporate some data such as seismic attributes and microseismic analysis when it's available for looking at properties such as frackability of our reservoir, and also look at things such as monitoring production using distributed temperature sensors and tracer surveys. This allows us to see where along the well we get the most production, which can better help us specify the properties of the fractures along the wells. So this information can also be used during history matching to be able to specify or to get a better understanding of the fracture properties along our well. We can also predict optimum well locations and design multiple coincident frac treatments using geomechanics, and we can get a better estimate of the stress states within the reservoir. This can be useful when we have situations such as simultaneous fractures, such as zipper fracs. So there's also been a variety of different lessons learned over the years. Oftentimes in the literature or at different conferences, we've seen statistical analysis of early time rates and EURs. However, different problems with these methodologies can lead to different oil field myths that can incorrectly become rules of thumb. So things such as comparing 30, 90, and 100-day rates versus cumulative well plots that haven't been normalized to flowing pressure or effective fracture properties. If we have different drawdown between different wells, obviously this is going to affect our production and affect our production rates. If we don't account for these things when doing the statistical analysis, we can see trends that aren't really there in the actual data. As well, EUR versus cumulative production plots can be even more misleading given the uncertainty in which EURs are generally being determined using analytical methods. We don't yet have the data to be able to forecast accurately for more than 5 or 10 years, since most of the wells have not been on for this long. So oftentimes these analytical methods may be misleading since we don't know what's going to occur in the future. And as well, looking at reservoir simulation, depending on the model design, if the physics are not right, it can lead to misleading results. When we are using our builder software, we always add in the logarithmically spaced grids around our fractures. However, if we don't use these logarithmically spaced grids and use larger grid sizes, oftentimes this can lead to misleading results. This is similar to using models that don't use radial grids around wells to model pressure transient tests. These can lead to misleading results since they don't model the transient inflow period. Basically, the assumption is steady state across the grid block. So here's a simple comparison where we compared the dual permeability simple method compared to the LSLR-DK method using local grid refinement with logarithmic spacing. Both cases produce the same amount of fluids. However, when we compare the pressures associated with each wells, the case with the dual permeability has a much lower pressure being predicted than the case where we've more accurately modeled it using the logarithmic local refinement. So as you can see, we can get misleading results if the model is not set up accurately. Over the years, we've also seen a lot of people moving towards simulation for doing their analysis and their predictions on ultimate recovery. We can see starting from around 2005 and 2006 is where people started looking more and more into simulation for modeling these types of plays. Over the years, we can see year over year, there's been an increase in the amount of users looking at modeling unconventional reservoirs using simulation. As well, in the literature, Oftentimes we use simulation for these processes. In 2014, we had a total of 216 papers using CMG software. That would be a low estimate since most papers don't actually specify which simulator was used. As well, 54 papers used this type of use CMG for modeling unconventional tighter shale plays, including 6 on gas injection. So in conclusion, I want to go over why we would use CMG for modeling tight and shale plays. So as you've seen, CMG has the physics required to understand and forecast production from unconventional wells and reservoirs. We have the ability to import geological models from geological modeling software to jumpstart your modeling workflows. We have the ability to add in fractures of varying geometries. So we can add in planar, complex, or even mixed geometry, propped and stimulated natural fractures into the simulation model. And we can also use microseismic data in the model building processes to define the size of your stimulated reservoir volume. Also, we only add the local grid refinement necessary to model the transient flow from the matrix of fractures, where we can use larger grids elsewhere so that we can run these models within reasonable run times. We can also easily and efficiently build single and multi-well models, as you saw within the demonstration. And we have the ability to parameterize matrix and fracture properties and dimensions when doing automated history matching and optimization. So with this, we can look at the entire search domain instead of being limited to a few half-lengths or spacings. There's also no need to manually pre-create these cases, as CMOST can automatically generate these cases for you. CMG also has a track record of continually enhancing our capabilities and workflows for unconventional wells and reservoirs. So I'd like to thank you all for coming to our webinar, and I'm going to hand it back to Anjani to start the question and answer period.
Thank you, Alex. We will now take up questions. If you have not submitted your questions, it's time to submit it now using the chat window on your screen. I see there are several questions that are coming in, and we'll try to answer them one by one. The first question is from Jay Safari, and he'd like to know how to account for changes in fracture conductivity with time in the model.
So we can do this in a couple of different ways. One is a more analytical technique where we can have a table of permeability in the fractures versus pressure. So as the pressure declines as we start producing, so will the permeabilities in our model, which overall will reduce the conductivity. We can also do this based on geomechanics. So if we do have changing stress regimes in the reservoir, we can also relate this to the permeability in our fractures and have that change over time as well.
The next question is from Roy Sandoval, and he'd like to know what is the format or template for inputting the hydraulic fracture data, that is orientation, fracture, half length, width, height, etc. to IMEX, and can I import this between different reservoir models?
So as you saw in the demonstration, there is the hydraulic fracturing window. So with that, we can define a template with all the different properties associated with it, so things like the permeability and half length. With the orientation, we based it on the grid direction, so we can select whether we want an I direction oriented fracture or a J direction oriented fracture. For taking it between models, currently there isn't an option in Builder for doing this. However, you can copy and paste data from one data set to the next, which Builder will then read in when it reopens the model.
The next question is from Jim Smith, and he'd like to know if using an element of symmetry in a horizontal well, when modeling one fracture penetrating multiple layers, is it still necessary to have multiple perforations before the wizard will refine through multiple layers?
With this, all we would need to do is have one well defined in there. If we are using an element of symmetry, we can reduce the model size down to one fracture. So we would just need enough well length to be able to add in that one fracture.
The next question is from Arun Kargoria. He wants to know, can we use this process with stars?
So this can be used with stars. Currently, I think the wizard is only available when looking at IMAX and GEM models. However, all the capabilities have been added to each of the 3 simulators. So you can base it off of, you can start off with an IMAX model and then copy the fracture properties from that IMAX model into a stars model. So this can allow you to do things such as thermal calculations in the fractures.
The next question is from Alberto Mezzatesta. He would like to know, in organic rich shales, how do we take into account the organic and inorganic portion of the rock in the reservoir description? They may both pertain to the rock matrix with different properties.
So right now they would both be listed as matrix properties. If we did have varying properties throughout the reservoir, we can adjust associated properties such as the absorption of our fluids by having variable or heterogeneous descriptions of these properties throughout the reservoir.
The next question is from Arshad Islam. He'd like to know is how to change the frac parameters such as permeability or porosity in runtime. Can we use operators such as multiplication or division to modify frac properties during the run?
So we can adjust the fracture properties during the run. I believe you will need to redefine the fracture properties if you're doing it for the hydraulic fractures. Matrix properties, you can just apply multipliers at a later date.
So the next question is from Chanta Salma, and the question is, how is leakage of fluids modeled during hydraulic fractures into over and underburden in CMG software?
So what we would need to do is incorporate the rock within that overburden and underburden. Really anywhere where the fluid can flow, that fluid will move. So if there is enough permeability in either the natural fractures or in the matrix, the fluid will just naturally flow based on the pressure gradient.
The next question is from Jeremy, and he'd like to know, instead of defining fractures on fracture spacing basis, can I create fractures at specific frac port locations?
So yes, you can do this. When I showed it in the demonstration, I just showed adding in a fracture spacing. However, if you do have a well in the field where you know exactly where the fractures are located, we can specify specific locations along the well based on the well address.
Question from Jorge, and he wants to know, when a fracture template is copied, will it also copy the relative permeability and water saturation specifications of the original template?
Typically it should. I did notice that when I was going through the demonstration that it wasn't copied in this instance. But for the most part in the other cases that I've run through, all the properties associated with the fracture should be copied from template to template.
The next question is from Jan, and he'd like to know, is it possible to use the same fracture definition to define a region with natural fractures in the reservoir and not link it to a well?
So if we wanted to define just a region of natural fractures, typically we would just do that by adjusting the fracture properties. So within a dual permeability system, we can define both the matrix properties and the fracture properties for a region. So if we wanted to have it unlinked to the well, we can just go to the fracture properties in that dual permeability system and adjust, say, the permeability or the porosity there.
Okay. The next question is from Wadud, and he'll like to know, what are your thoughts on modeling refracturing? That is, modify frac conductivity or addition of extra new fracture areas.
So with our newer version, we can easily model this. We can specify an initial set of fractures that we would start with our first simulation. If we then go in to add in the fractures at a later time, we can quickly go back to our well, select a new date, and add in those additional fractures. One additional benefit of using it this year is now the refinement will only be added when we do that refrac. So you would have some refinement for your initial fractures, and the additional fractures that you add at the refrac date will only be added at that time. So this allows for faster simulation up to that point, since we have less grid blocks in the model.
The next question is from Samin, and he'll like to know, will the CMG gem add hydraulic fracture propagation in natural fracture shale so that we have a better prediction of SRV?
So we can currently do this with our Geomechanics package. What we would use is the Barton-Bandis method, and we would define where we would want the fractures to propagate. So we would sort of have a predefined region where it would be possible. Then depending on the stress regimes in the reservoir, when we start injecting, the fractures will be opening, as you saw on that previous slide about halfway through the presentation.
The next question is from Hong Gang, and he'd like to know, we have interest in to simulate and track the fracturing fluids during the fracturing simulation, and also to track production times. How can CMG model and quantify fracture treatment fluids?
So typically what we would do is we would initialize the fractures with the amount of fluid that was injecting during the frac treatment. If we'd like, we can define the water in a couple ways. We can just have one water component, or if we wanted to compare the water native in the reservoir compared to the fracture fluid, we can define two water components, which allows us to more accurately track that frac fluid. So once we've initialized our model with the water in those hydraulic fractures, we can then model the production of that frac fluid over time.
So the next question is from Adele, and he wants to know what happens when LGR overlaps between two wells. In general, builder accepts it, but IMEX could stop. Can you add further to that?
So when we have these overlaps, we need to take care to specify the half lengths in those regions so that they basically butt up against each other. So what we would do is we would define our fractures for one well, and then if we do think that there's a region where we would have intersections of the fractures, we may adjust the second fracture half length so that they just come up right in contact with each other without that overlap.
The next question is from Gerardo, and he will like to know, can you elaborate a bit more on how CMG approaches the fracture propagation? Is it entirely dependent on Barton-Bandis model, or do you use some other way of doing it?
Currently, it will be based on the Barton-Bandis model. So like I said earlier, it will depend on the stress regime in your reservoir. So we can set in our initial stress conditions, and then as we inject the fluids, the simulator will model this, or will monitor the stress conditions, and if it goes over a certain threshold, then we'll have fracture opening, which we would then have changes in permeability and properties in the reservoir.
The next question is from Kashif. Can we use unstructured grids in order to provide geometrical flexibility, especially for reservoir elements that needs to be upscaled?
So currently we don't allow for unstructured grids. All of our grids currently are structured. We can use the fracture networks for defining different types of fracture geometries though. So if we do find that it goes off on an angle away from the typical fracture propagation direction, we can use these type of networks to sort of follow that pathway.
The next question is from Mostaba. Could CMOST be coupled with the reservoir simulator to change fracture configuration automatically?
So yes, this is one of the ways we can use CMOST. We can define really any of the properties related to the fracture. So for example, if you wanted to change the half length, all we would need to do is select that half length as one of the properties that I want to modify. And then when we start running CMOST, it will automatically select a new half length, and the simulation model will be regenerated using that new sizing or configuration.
The next question is from Ismail. Can we use dual porosity, dual permeability to model secondary fracture with matrix segmentation?
I'm not exactly sure what you mean by matrix segmentation, but we can use the dual permeability model to model both the natural fractures or secondary fractures as well as the matrix. So it allows us to completely separate the properties between those two different regions.
So I see there are a lot of questions that are coming in the chat window, and due to time restrictions, we may not be able to take on all the questions in this forum, unfortunately. But a CMG representative will follow up with your questions individually in a short while, maybe in a day or two. I hope you have gained a better understanding of how to include hydraulic fractures in your simulation models and how CMOST can be used to optimize your reservoir. If you like to improve your simulations and you'd like to know more about some of the methods described today, CMG offers multitude of training courses for all skill levels. For those of you who are interested in unconventional modeling, we frequently offer modeling of shale, tight oil, and gas reservoir courses in our Calgary, Houston, and UK offices. We also offer company-specific customized courses on a variety of subjects all around the world. For more information on our training course offerings, I'd like to invite you to visit our website at cmgl.ca. If you have any questions related to the material presented today, or you'd like to know more about our product offerings, please do not hesitate to contact us by email to sales@cmgl.ca. Again, from CMG, I'd like to thank you all for joining us on this webinar on latest advancements in advanced modeling and optimization of hydraulic fractures. Thank you.